Hello. In previous video we have dealt with potential barrier. This is one of the important application of Schrodinger wave equation, that is a one dimensional problem. We have illustrated what is potential barrier and what we have to do. Now we have to solve some equations which we have not solved in previous video. In this video we will solve that equations and we will fulfill our aim. Now recalling in short that the potential for was like this. This was potential for how it looks like one dimension x, this is for one dimension, and this is what we have shown for potential. Shape of potential. Now as we know that this is potential Vx and this is potential height V naught 0 to a. We have considered psi 1, psi 2, psi 3 and these wave functions format we have written from previous video. We can write down psi 1, psi 2 and psi 3. There was particle moving from left and we have to consider that particle motion using classical view and quantum mechanical view, and we have to differentiate between them. What we observe for incidence wave, we have taken A to the power ik1x, when that reflect B it is power minus ik1x, okay, and when it transmit in second region, region first, region second and region third. So here this was C e to the power ik2x, and here for reflection D it is power minus ik2x, and for again in third region E to the power ik1x, because momentum is same now in this regions, region first and third, okay. And also we see that the wave in the format like this. That is the wave associated with particle, how it moves, its nature. So drawing here like this. Acceleration. So we have discussed these in previous video. Now come across our main concern for psi 1 A e to the power ik1x plus B e to the power minus ik1x for psi 2, C e to the power I k2x plus d e to the power minus I k2x, and for psi 3 e to the power I k1x, since there is no reflection from third region, therefore it is the same. Now we will apply, we have to solve RNT, quantum mechanical reflection coefficient and transmission coefficient. We have to see, does it exist? Okay, so now we will apply boundary conditions. What are boundary conditions now? Boundary conditions in this case at point 0 and a. So psi 1 and psi 2 both function are equal at 0, and we know that also when psi is continuous function of x at this point, then its first derivative also, that is dy psi 1 upon dy x, and first derivative of this wave function. As same at point a. At point a, psi 2 and psi 3 will continuous function of x, so psi 2a and psi 3a. After its first derivative also, dy psi 2 upon dy x and dy psi 3 upon dy x. So using these boundary conditions, we will apply these conditions using these equations. So after applying, we will get 4 equations, and we will solve that 4 equations and finding relation between constant to get the value of RNT. Okay, so now we have to solve and we have to obtain equations. So okay, now from this obtain equation, when psi 1 0 is equal to psi 2 0, so from here you will put here 0 0, that is 1, only a plus b is equal to c plus d will remain. After here, for second, we have to differentiate this function. When you will differentiate, what we get? We get I k1 a e to the power I k1x minus b e to the power minus I k1x, because minus I k1x, I k1 we have taken here common, and this will be equal to of psi 2 derivative he from here, that will be I k2 again common, you will get c to the power I k2x minus d e to the power minus I k2x, but we have to put 0 also. When we will put here 0, this will become 1, this will become 1, this is 1, this is 1, only constant will remain, and this I will cancel out. So finally, using this relation, what we get? We get k1 in bracket a minus b, k2 in bracket c minus d. Okay, may I disturb now? This is for one illustration. This is our main result by applying condition number second. Now apply condition third. Again easy, we have to put only a instead of x here. Here for psi 2 and psi 3. So obtain equation number third. C e to the power I k2a plus d e to the power minus I k2a is equal to e to the power I k1a. This is again third. Now applying this fourth relation, using these, first find derivatives. So dy side upon dy x from here ik2 will get from both terms. So ik2 will be common, c e to the power I k2a minus d e to the power minus ik2a is equal to ik1 e to the power minus I k1a, because we have to put a also. So this is what we have achieved fourth equation by applying this. I cancel out. Okay, so using these four conditions and these relations, we have obtained four equations. Now using these four equations, we will find relation between coefficients to calculate R and T. For T, obviously we have to find E by A, and for R, because what is transmission coefficient? This is transmitted part, this is total, so total by transmitted. And for reflection coefficient, we will find B by A. Okay, so write it to solve now. Now writing first these two equations to solve A and B in terms of C and D. First, find A and B in terms of C and D. For this, consider A plus B is equal to C plus D and A minus B. Yes, K1 will shift here. So K2 by K1, C minus D. Now we will add it and subtract it to get A in terms of C and D. First add it, you will get 2A. Here C will be common, so this will be in bracket 1 plus K2 by K1, and here when D will be common, then 1 minus K2 upon K1. Calculate A. C by 2, 1 plus K2 upon K1 plus D by 2, 1 minus K2 by K1. As same, we will minus these equations. When we will minus these equations, what we get? This A will be cancelled out, so we will get 2B. 2B is equal to, for minus we will take common C, so we get 1 minus K2 by K1 will plus D 1 plus K2 by K1, and obviously when this 2 will transmit here, shift here, C by 2 and D by 2. So what we have found here, value of A and B in terms of C and D. We will use it further. Okay, now find C and D in terms of E from these two equations. Find C and D in terms of E. We are using here A and B in terms of C and D. After finding C and D in terms of E, we can put that value here so that we can obtain relation between A and D to calculate T. Okay, proceed first now. So writing two equations again. C e to the power I k2a plus t e to the power minus I k2a is equal to e to the power I k1a, and this is shift k2 to RHS. C e to the power I k2a minus t e to the power minus I k2a is equal to k1 upon k2 e to the power I k1a. So we will first add it and we will minus also. So first add it. After adding, what we get? We get this will be cancelled out, this term. So we get 2c e to the power I k2a is equal to here e to the power I k1a 1 plus k1 upon k2. Okay, so what is C? C will be e by 2 shift towards here in denominator e to the power I k2a, then shift in numerator, that is e to the power minus I k2a. So we can write e I k2 minus k1 a, is it? And this term 1 plus k1 by k2. So this is what we have find. Now doing same thing for minus. Take minus, then this term will be cancelled out, this term, and this will be added because sign will change. So 2d e to the power minus I k2a is equal to e to the power I k1a common, and we get 1 minus k1 upon k2, and as same we can shift this 2 here. So what is d now? D will be d is equal to e by 2 this one, shifting this exponential term to denominator, then shifting to numerator. What we get? E it is power I k1 plus k2a 1 minus k1 upon k2. So this is what we have find d, c and d in terms of e. Now this c and d in terms of e will be put here so that we can find relation between a and d and b and d. Okay, now putting value of c and d in equation A so that we can find relation between a and d. For this we write a is equal to, since a is equal to what? A is equal to c by 2 1 plus k2 upon k1 plus d by 2 1 minus k2 upon k1. Just we have found this. Now since the value of c and d, what is c and d? The value of c and d was found to be e by 2 e to the power I k2 this is k1 minus k2 a 1 plus k1 upon k2. The d was found as e by 2 e to the power I k1 plus k2 a 1 minus k1 upon k2. This c and d we will put here. Now putting this, so we get e by 4 e to the power I k1 minus k2a. Now this term and this term 1 plus k1 upon k2. We have put in the value of c, and this to the 4 on this term also 1 plus k2 by k1, and as same we will put here d also. So putting this d here, that will be plus e by 4 e to the power I k1 plus k2 a 1 minus k1 upon k2 and 1 minus k2 upon k1. Okay, now we have to solve this and we will find relation between e and 4. So some simplification required. Now continuity. So a, taking e by 4, and here common is e to the power I k1a from both terms. So what is remaining? E to the power minus I k2a. Here taking k2 and k1 as LCM, so we will get k1 plus k2 whole square upon k1 k2 plus here e to the power I k2a, and taking minus 1 from this term, so that this will become k1 upon k2 minus 1. So we will get k1 minus k2 from here and k1 minus k2 from here also. So k1 minus k2 whole square upon k1 k2. Yes, by taking simple LCM. Okay, and this minus 1 can be multiplied here easily. Now again a is equal to what? E to the power I k1a by 4 k1 k2 again common. Now we want to open this expansion. K1 square e to the power minus I k2a k2 square e to the power minus I k2a and plus 2 k1 k2 also e to the power minus I k2a. Okay, now this we have to open this one also, so we have to multiply with this term also. So minus k1 square e to the power I k2a minus k2 square e to the power I k2a and plus 2 k1 k2 2 k1 k2 e to the power I k2a. Okay, now solving further, taking some common from this term, this and this, then from this and this, and this and this. Okay, so e to the power I k1a upon 4 k1 k2. Now taking k1 square, k1 square, what is remaining? E to the power minus I k2a minus e to the power I k2a, and for k2 square e to the power minus I k2a minus e to the power I k2a, this and this, and after this plus 2 k1 k2 e to the power minus I k1a plus e to the power I, this is k2a and k2a, bracket closed. Okay, now from here we can write down now, since taking this here, this term, if we will get, yes, same, so taking common e to the power I k1a upon 4 k1 k2, and from here k1 square plus k2 square will common, and e to the power minus I k2a minus e to the power I k2a plus 2 k1 k2 e to the power minus I k2a plus e to the power I k2a. Okay, solving further, now using this exponential terms, converted into sine cos. As we know that, yes, first know this formula, that e to the power I x plus e to the power minus I x by 2, this can be written as cos x, and e to the power I x minus e to the power minus I x by 2i, this is sin x. So if you look, so this portion can be converted into cos terms, and this portion can be converted into in terms of sine. Okay, so finding here, if we will put here I k2a plus e to the power minus I k2a, suppose the value of x is k2a by 2 is equal to cos x, it means that this quantity will give us 2 cos k2a, because x is k2a. So writing here, this will become 2 times of cos k2a. What about this one? We can take here also x is equal to k2a, so this will become e to the power I k2a minus e to the power minus I k2a is equal to 2i sin k2a, taking minus e to the power minus I k2a minus e to the power I k2a is equal to minus 2i sin k2a. So this value will be, yes, taking this minus, first we will take common minus here, then this value minus shifted here, so this value will imply minus 2i sin k2a, which we can put for this. So this term will treat as minus 2i sin k2a. So rub this now, this was for understanding. Now writing out a question, what is e to the power, this is equal to a I k1a upon 4 k1 k2 k1 square plus k2 square. Obviously this 2 Okay, for starting here, minus 2i sin k2a plus 2k1 k2 2 times of cos k2a. Now this 2 will be common and we can take, so this will become 2 power I k1a upon 2k1 k2, because this 2 will be getting common, so we get k1 square plus k2 square minus I sin k2a plus 2k1 k2 cos k2a. Okay. Now as we have to find t, for t we have to find e by a, so calculate e by a from this relation e by a. So shifting this, we get 2k1 k2, this will be in denominator, shifting up e to the power, this will be minus I k1a, and this will be in denominator by k1 square plus k2 square minus I sin k2a plus 2k1 k2 cos k2a. So we have find this e by a. As we know that, what is t? T is e by a and e star by a star, that is complex conjugate. So we have to find complex conjugate of e by a. Okay, so finding e star by a star, its complex conjugate. So here is I, this will become minus, so 2k1 k2 e to the power I k1a upon k1 square plus k2 square, I become minus, so plus, this will be I sin k2a plus 2k1 k2 cos k2a. Now since we have to find t, this is what we can write in short, mod e by a whole square. So calculating t, this into this as in formula here. So when you multiply, in numerator multiplication we get 4k1 square k2 square by, here this is in the form of a plus b and a minus b, so we will get a square minus b square, that is this square and this square. So k1 square plus k2 square whole square, and I square minus 1 minus plus, so sin square k2a plus this also 4 k1 square k2 square cos square k2a, and this can be converted into, well, in terms of sine. So writing once more that cos square k2a, this will be 1 minus sin square k2a. So writing this 4k1 square k2 square, what actually happens here is 4 k1 square k2 square cos square k2a, so multiply with here also 4k1 square k2 square and minus 4 k1 square k2 square sin square k2a. So this term, yes, this term, two terms, so for this term and this term, this both term, because this is k1 square, this plus k2 square, this plus 2 k1 k2, this is in minus. So what we get finally? We get k1 square sin square k2a plus k2 square sin square k2a minus 2 k1 square k2 square sin square k2a. That is, it can be written as what? K1 square sin square k2a plus k2 square sin square k2a and plus 2 k1 square k2 square, and here is minus 4, so that will be minus 2 k1 square k2 square sin square k2a plus 4 k1 square k2 square, and this can be written as k1 square minus k2 square whole square. So finally writing T 4 k1 square k2 square upon k1 square minus k2 square whole square sin square k2a plus 4 k1 square k2 square. So this is what we have obtained transmission coefficient. Now we have to find reflection coefficient. Okay, so we have find quantum mechanical transmission coefficient. Now we have to find quantum mechanical reflection coefficient. For that we have to find relation between B and A. So as we have solved this one in the starting portion, so this B in terms of C and D and this C and D in terms of E. So this C and D we will put here so that we can find value of B in terms of E. Okay, so we get value of B as B is equal to E by 4 e to the power I k1 minus k2 a 1 plus k1 upon k2 1 minus k2 by k1 plus e by 4 e to the power I k1 plus k2 a 1 minus k1 upon k2 and 1 plus k2 by k1, as we have shown that equation. Nothing, we have what? We had a value of B in terms of C and D and C and D in terms of E. We have put it that value and obtained this equation. Okay, now taking some common, E by 4 e to the power I k1a, it is common, so e to the power minus I k2a. Again here taking LCM in numerator a plus b minus b, so we can write k1 square minus k2 square upon k1 k2, and here e to the power I k2a, also taking minus 1 from here, so that k1 upon k2 minus 1. So again here also k1 minus k2 k1 square minus k2 square upon k1 k2 using a plus b and a minus b wholes. Okay, Now this minus 1, okay. So taking this also common, take outside, e by 4 e to the power I k1a k1 square minus k2 square upon k1 k2 in bracket e to the power I k2a, and this minus e to the power I k2a. Now as same, this is also converted into what? Just we have shown that e to the power ix minus this upon 2i is sin x, or this can shift it here, so 2i. After taking minus, so it is power minus x, it is power ix is equal to 2i sin x, shifting this minus here, so this will become like this. So when x is equal to k2a, this will become minus 2i k2a, which is here case. So this will become minus 2i sin k2a. Okay. So writing down e to the power I k1a k1 square minus k2 square minus 2i sin k2a by 4 k1 k2, this is 2 times. So now this is b in terms of e, and when we were finding transmission coefficient, then in that procedure we were relating a and d. From there you can notice that that portion was just we find in that case that a is equal to e to the power I k1a. This we have find just this one when we were calculating transmission coefficient in bracket k1 square plus k2 square minus psi sin x plus this is k2, this is k2a plus 2 k1 k2 and cos k2a. Just we have find this equation when we were solving transmission coefficient. So now we will divide these so that we can find relation between b and d. Now obtaining b by a. So when we find b by a, this term will be cancelled out, this e cancel out, this exponential e to power I k1 cancel out, 2 k1 k2 be cancel out. Now here this and this term will remain, so we will write k1 square minus k2 square minus I sin k2a upon this by dividing these two. So this also k1 square plus k2 square, and here minus I sin k2a plus 2k1 k2 cos k2a. Okay, and we know that for to calculate r we need b by a and b star by a star, that is complex conjugate, and r is equal to this. It is what? Quantum mechanical reflection coefficient. So finding complex conjugate b star by a star, k1 square minus k2 square, this will be, yes, negative for 5, that will plus I sin k2a by k1 square plus k2 square I sin k2a plus 2k1 k2 cos k2a. So find r. What will be r? Yes, this is multiplication of these twos. So multiply now. So numerator, first see numerator, what we get? We get k1 square minus k2 square whole square sin square k2a I square minus 1 become plus upon, now here this is in denominator, this is in the form of a plus b and a minus b, so a square minus b square, writing again k1 square minus that is plus k2 square whole square, and this is sin square k2a plus 4k1 square k2 square cos square k2a. Again converting this term into sin square, that is we will use cos square k2a is equal to 1 minus sin square k2a. So as we have converted in transmission coefficient, we will convert this also. So what will happen? This 4 times, because we will get here 2k1 square k2 square sin square k2a, and from when we will use this relation here, we will have minus 4k1 square k2 square sin square k2a. So this will be when solved we get minus 2k1 square k2 square sin square k2a. So that will be k1 square minus k2 square square sin square k2a by k1 square plus k1 square sin square k2a plus k2 square sin square k2a, and that will be minus 2k1 square k2 square sin square k2a plus 4k1 square and k2 square. Okay, now this term will be k1 square minus k2 square whole square, k1 square minus k2 square whole square sin square k2a by k1 square minus k2 square square sin square k2a plus 4k1 square k2 square. So this is what we have solved quantum mechanical reflection coefficient, and just we had obtained also quantum mechanical transmission coefficient, that was t is equal to, yes, we have achieved this equation just before some time, this by k1 square minus k2 square whole square sin square k2a plus 4 k1 square k2 square. Okay, so this t is proved just before and these are just now. Now what we see that we have the value of quantum mechanical reflection coefficient as well as quantum mechanical transmission coefficient, and obviously by definition we know that the value of r plus t, when we calculate, what we get, k1 square minus k2 square whole square sin square k2a plus 4 k1 square k2 square by k1 square minus k2 square sin square k2a plus 4 k1 square k2 square. Now yes, obviously this will be cancelled out, whole terms, numerator and denominator, and what we get 1. So by definition r plus t is equal to 1. It means that our expression is absolutely correct. Now we will come across picture. So by whole calculation, that is after calculating r and t, now we infer that according to quantum mechanical view we get total this that is the reflection coefficient and transmission coefficient also. Therefore we get here what? Wave nature of the particle in all three regions, not of only transmission but also reflection as well. But when we see in case of classical view, then according to classical view, since energy of the particle is higher than this potential barrier, so according to classical view there should be not any reflection coefficient. But this is not in agreement in quantum mechanical view. This is what we have differentiated. Now in next video we will solve for case second, that is when energy of the incident particle will be less than this potential barrier, and we will see that case also. Thank you.